You see Philip Rivers going back to his.
Welcome, welcome.
The Suns are down by 50.
He's like,
Or 30 to under.
But they broke the chain.
Dude, they actually
So,
they like the
Quarterback
best
stinks
of
in
all
there.
time.
Quarterback got injured, so.
They get all the fouls.
we've got an exam coming up.
It's just like shade changing. That's
Foul hater.
yeah, it's crazy.
And
Two first round picks.
tonight I'd just like to answer your questions, get you ready for that experience. So, what's brought you out on a lovely Wednesday evening when you could have been watching Netflix? What questions do you have? Back in the back there. Be right with you.
Last one thinks.
Yes. If something is going around in a circle, like on a wheel, let's say that piece of chewing gum that we put on that record player disc that's going around. That has a velocity that is tangent to the circle. Oh, I didn't draw it very tangent, did I? Let me start over. If I look at the circle that thing is traveling around, its velocity will be tangent to that circle. And if that is going around at a constant speed, then it will have a centripetal acceleration towards the center of the circle. But that's a change in the linear velocity. If this is going around at a constant speed, the omega would be constant, and that means that the alpha would be zero. The angular acceleration would be zero. Now, if this were speeding up, and we call this v tangential because it's tangent to the circle that it's going in. If this record player were speeding up faster and faster each second that goes by, then there would also be an acceleration tangential in the same direction as the velocity itself. That's the gas pedal acceleration, okay? Whereas this one is the steering wheel acceleration. But both of these are linear accelerations. They are the change in the linear velocity that happens in the next second. And so this one is going to be due to the fact that a second later, it's going to have a different direction. And this one is due to the fact that a second later, it's going to have a different length. It's going to be longer.
Sorry.
Okay. Whereas alpha just has to do with the spin rate, nothing to do with the linear velocity vector. That answer your question? Okay. And I had another question. You had a question? Yes.
This portion of the same place.
Oh, okay. Let's go back to that first tutorial. And you remember that when we had a ball going up the ramp and slowing down to a stop, we found that the acceleration These were velocity vectors. We found that the acceleration was down the ramp. Even at the turnaround point. And that's because acceleration is a change in velocity. And for a change, I need to have two different points. If I look just a little bit before the turnaround point, it was going up. A little bit after the turnaround point, it was going down. I call that V initial and that V final. My acceleration is going to be V final minus V initial over the time interval involved. Well, I find that V initial minus V final minus V initial, I find by putting them tail to tail. And then I ask, what do I have to add to that vector up the ramp to get a vector down the ramp? That's my change in velocity. Well, if I have a wheel that is turning, say, counterclockwise, that's going to have an omega that is out of the page by right-hand rule for omega. If that wheel slows to a stop and then turns around and goes the other way, well, the omega final will be out of the page. Well, again, the alpha is the omega final minus the omega initial divided by the time. Now, this is a little bit harder than the going up the ramp example because we have to think in 3 dimensions. If I'm starting with a vector, an omega vector out of the page, and then a moment later it's into the page, what kind of change is that? What do I have to add to something out of the page to turn it into something into the page? I've got to add something into the page, okay? Now, another way of thinking of it is acceleration is how much the velocity is changing. If I throw a ball up into the air, the acceleration can't be 0 at the top at the turnaround point, or it would just stay there forever. It'd hover. Well, the same thing with this example of the wheel. As she's going up, as she was going up, the wheel was turning this way, and then it slowed to a stop, and then it was turning that way. If at the top my alpha were 0, it'd just stay there. She wouldn't turn around and go back the other way. Does that help? Okay. Yeah. Coming.
Can you give a brief overview of buoyancy and some of those concept questions about density?
Yes. The best tool you can have in your toolbox for a buoyancy problem is the understanding of what Archimedes' principle really means. It's that the buoyant force is just the weight of the fluid displaced. And those words, I'm an old man and I've been doing this a long time, and those just seem to fly past beginning students. What? I don't know what that means. Well, you know what weight is. You know how to find the weight of something. If something had a mass of 2 kilograms, you just multiply that by 9.8, call it 10, and you'd say, well, that weighs 20 newtons. Okay. And the only wrinkle in these problems is that we tend to deal with things in grams.
Can you scoot it down?
And like I said in class today, if I told you the mass of some things in grams, you'd be able to find the weight really quickly. There would be an extra step. I mean, when I told you I got something that has a mass of 2 kilograms, you just multiplied by 10. But I gave it to you in kilograms. And so you have to start with kilogram. And so I take this 600 grams and I say, well, I move the decimal place 3 places to the left, and that's 0.6 kilograms. And then to find the weight of that, I say the weight is just the 0.6 kilograms times 10 newtons for each kilogram, or 6 newtons. Now, let's look at the last half of Archimedes' principle. The buoyant force is the weight. The weight of what? The weight of the fluid displaced. And that's another piece where beginning students start to struggle, is that, what do you mean liquid displaced? Well, if something's submerged, if it's under the surface, where it is now, liquid used to be, had to go elsewhere. That's displaced. Okay? If something's floating, it's only this part here that is displacing liquid. Okay, the part below the surface. Now, here's the next wrinkle, and that is when we have something submerged and we ask, well, how much liquid got displaced? Well, it's the volume. Okay, if this had a volume of 200 cc's, then 200 cc's of liquid had to go elsewhere, were displaced. And so you want the weight of 200 cc's of liquid. Well, gee, Greg, if you gave me the grams, I already did that problem. If I had the grams, I could just turn that to kilograms, multiply by 10, and get the weight. But converting from cc's to grams is really, really easy. It's through the density equation. The density is equal to the mass divided by the volume. And I can rewrite that as mass is equal to density times volume. Okay. So if this object were in water, then the density would be 1 gram for each centimeter cubed, and I got 200 centimeters cubed. Okay. And so that's going to give me 200 grams. And water's what you pray for. You know, let there be water on this exam. That would be lovely, lovely. Ain't gonna happen. Ain't gonna happen. I happen to know. Okay. So let's say this is heavy cream. If it's heavy cream, the density is 1.5. Okay, well, it's not that different. I just say, well, now the mass is equal to the density of 1.5 grams for each cc, and I got 200 cc's. Well, that's going to give me 300 grams. So if this thing were submerged in water, it would have a buoyant force of 2 newtons. If it were in heavy cream, it would have a buoyant force of 3 newtons. Does everyone see where I got the 2 and the 3 there? Questions? Everyone okay? Okay. Now, the other possibility is alcohol, and you know, and we're at BYU, so that's just obviously rubbing alcohol. I mean, it's not any other kind of alcohol. And so that's going to have a density of 0.8. And so in that case, I would say, well, the mass is equal to 0.8 grams for each cc, and I have 200 cc's. Well, that's gonna be 160 grams. And so in that case, I'm going to have a buoyant force of 1.6 Newton. See if your neighbor's okay with what we're doing there.
Would be 1.6.
Now, if something floats, you get a bonus. You get a freebie, an extra. And that is, if something floats, freely floats, such that there's only one force up, the buoyant force, and one force down, the weight force, and it's not going anywhere, acceleration 0, they got to be equal. And so if something's freely floating, it's got a buoyant force equal to its own weight. Now that also means that it's displacing enough fluid to equal its own weight, because Archimedes' principle still applies. But it's got to be freely floating. You had a homework problem where you had a situation where there was a block A that was floating with 3/4 of its volume underwater. But it wasn't freely floating because there was this block B, like an anchor, hanging off the bottom. And so when I drew the free body diagram for block A, I didn't just have one force up and one force down. I had one force up, the buoyant force, and I had two forces down. I had the weight of block A, and I had the tension in that string pulling down. And so that's not freely floating. And so you can't use that second tool from your toolbox. It's only when it's freely floating. Am I getting close to answering your question? Okay. I hope that you'll visualize what's going on instead of just plugging into that formula that's on the front page of the exam. Because that formula on the front page of the exam is exactly the same as what we're doing. I mean, we're using this formula here to find the mass, and then we're taking that mass and we're multiplying that by G, by 9.8, let's call it 10 newtons for each kilogram. The problem is, if you just plug into the formula, you get a mass in grams and you forget to convert that to kilograms before you multiply by G. And so you get an answer that's 1,000 times too big. And, you know, being off by a half or a quarter is okay, but when you're off by a factor of 1,000, that's wrong. That's just wrong. Picking wrong. Okay. So, question, yes.
Can you go for like the 11 arms?
Okay. So if I have that drawbridge problem where I have this drawbridge, that's my pivot there. If I'm looking for the torque due to this weight force, one way to do that is to just extend that weight force in both directions forever. And we call that the line of action. in other words, the line along which that force acts. And the lever arm is just the distance from the pivot to that line of action that comes in perpendicular. Okay? And so if I can find that lever arm, then the torque due to the weight is just going to be the lever arm times the weight. Full stop. Now, since that problem had a 24-meter drawbridge, this distance here is 12 meters. And we were told that this was 53 degrees. And so that tells me that L is going to be equal to 12 meters times the cosine of 53 degrees. Okay. And so that means that my torque is going to be 12 meters times the cosine of 53 degrees times the weight. Well, let's do this same problem with the useful force method. If I use the useful force method, I break this weight force into two parts. The part of the weight that's perpendicular to the drawbridge and the part that's parallel to the drawbridge. Okay. Now that angle there, we remember from when we were dealing with force problems on a hill, that angle there has to also be 53 degrees. And so that means that my perpendicular part of the weight is going to be the total weight times the cosine of 53 degrees. Well, in this case, I'm going to use all of the position vector, the whole 12 meters, and just this part of the force that's perpendicular to that position vector. In other words, the torque is going to be 12 meters times the perpendicular part of the weight. Well, we just said that the perpendicular part of the weight, I'm going to plug in here, is W times the cosine of 53 degrees. Well, you see, I get the same exact answer, regardless of which of those approaches I take. In both cases, it's going to be 12 times the weight times the cosine of the angle. Okay. Now, a problem like this, you really don't see a great advantage with one approach over the other. There are some examples where one is much easier than the other. Yes, sir.
Can we go over the problem that's like a submerged stick and like you have to find the tension force on the rope?
The homework problem?
Yeah, or we did one in class too, just like one where like it's like a buoyant force and you have to find tension.
So guide me a little here.
I think it was problem 4 in the homework last night.
Okay, you want to work that problem?
Yeah. Yeah.
So in that problem, we found that if we hold down with 2 newtons here and 6 newtons there, we were told that this meter stick had a weight force equal to 4 newtons and that it had a volume of 300 cc's and that it was submerged in water. And we were told that if we attached this would be T2, if we attached a third string some distance R from the left side, and we pulled on that string with just the right force at just the right angle, that meter stick would stay put. It wouldn't go up, it wouldn't go down, wouldn't go left, wouldn't go right, and it wouldn't rotate. Now, let me ask you, this is the homework. This is the problem we worked in class. You want to work that one or you want to change the numbers?
Change.
Your choice. What's that? Change the numbers? Okay. Let's make that 5 newtons. Let's make that 8 newtons. And we'll make this 6 newtons. And we can make this 200 cc's. That fair? Okay. So we're looking for 3 things. We're looking for the magnitude of T3, and we're looking for that angle. And we're looking for R. Well, let's break up T3 into 2 parts. Let me call that Ty, and I'm going to call that Tx. And now my goal is to find Tx and Ty and R. Because I know if I can find Tx and Ty, that the magnitude of T3 is just going to be the square root of Tx squared plus Ty squared. And I know that that angle is just going to be the inverse tangent of the opposite side over the adjacent side. So once I have Tx and Ty, I know what the original things I was looking for, the magnitude of the tension force and the angle. Okay? So got 3 unknowns, so I need 3 equations to solve for 3 unknowns. My first equation is going to be all the force left is equal to all the force right. And that tells me, since I've only got 1 force left and 1 force right, that Tx is equal to 8 newtons. Everyone see where I got that? That's my first equation. My second equation is all the force up has to equal all the force down. Well, we don't have all the forces on our free body diagram yet. Which one are we missing?
Buoyancy.
The buoyant force, okay? And again, that buoyant force is equal to the weight of the fluid displaced. And lo and behold, it's water. That's just simple, easy peasy, okay? I know that it displaces its full volume because it's submerged. All 200 cc's are pushing water out of the way. And I know that 200 cc's of water is easy to work with. It's just 1 for 1. So that's 200 grams of water has been pushed out of the way. And 200 grams is just another way of saying 0.2 kilograms. And if I ask you how much does that weigh, you'd multiply by 9.8, call it 10. and you'd say 2 newtons. And so I've got a buoyant force of 2 newtons. Okay? So if I balance all the force up with all the force down, I've got Ty that's up. I have 2 newtons that are up, and that's it. And then down, I've got 5 newtons from T1, and I've got 6 newtons from the weight. And that means Ty plus 2 has to equal 11, and that means Ty is equal to 9 newtons. Okay? Well, now I can go and I can calculate what T3 is, and I can calculate what the angle is. What we're missing is R. And R just screams out pirates. Okay. It screams out torque. We got to balance torque. And so I'm going to choose my pivot to be the left end. Well, why, Greg? Well, this meter stick's not rotating about any point. I'm free to choose any point as my pivot point. I chose the left-hand side because the homework problem wanted to know how far from the left side should we attach this third string. And if I put my pivot over here, my distance to the pivot is not going to be R, it's going to be 1 meter minus R, and then I'm going to just need to do more math. It's just going to be messy. So I'm just going to choose it over here to make the math easy. If I look at what gives me torque about this pivot, T1 gives me no torque because it acts at the pivot. T2 gives me no torque because if I draw its line of action, it goes right through the pivot. So there's no lever arm. If I look at TX, I drew TX up here, but these two forces are really part of this string pulling right here. And so TX is really pulling right at this point. And so again, it gives me no torque about that pivot. The only ones that give me torque about this pivot are Ty, the buoyant force, and the weight. And then I just have to say, which of those are clockwise torques and which of those are counterclockwise torques? Well, if I pretend that there's a hinge right here, forcing this meter stick to rotate about that hinge, Ty is giving me a counterclockwise torque. The buoyant force is giving me a counterclockwise torque, whereas the weight is giving me a clockwise torque. So, so that I can see the picture and not have to move the page up here, let me just carve off some space and say, well, the clockwise torque was just the weight, 6 newtons times a half meter. The counterclockwise torque, I have Ty, which we said was 9 newtons times R. And then we had the buoyant force, which was 2 newtons times 0.5 meters. Well, this is going to give me 3 meter newtons is equal to 9 newtons times R plus 1 meter newtons. If I subtract both sides, 1 from both sides, I get 2 meter newtons is equal to 9 newtons times R. And that gives me an R equal to 2/9 meters. The newtons cancel. That work for everybody? again, we have a whole branch of science called equilibrium. And if you were going to be a structural engineer or an architect, you would take all sorts of classes that are called statics. And in those statics classes, they would just work these problems where things are not moving up or down or not rotating. Because when you're building a big old high rise or a house, you don't want a linear acceleration and you don't want an angular acceleration. You want it to be static. And so these problems, for something as messy as a high rise, can be really, really ugly, where you would need a complicated computer kind of modeling program to help you figure out all the forces that need to be acting. Okay. But we deal with simpler things. Reese?
I wondered if you had access to the sample exams.
Yes.
Could you help me with the second one that has the girl with?
Certainly, yes.
Thank you.
Not this one. Okay. Currently, I'm team teaching this class with Adam Benyon. It's been a delightful experience. Back in Montana, I had an opportunity on several occasions to team teach the class with Shannon Willoughby, and that's the best picture I could find of Shannon there. And so she's on this skateboard that's been designed to be level going uphill, but only certain hills, and not so friendly going downhill. So we're told the front wheel radius is 0.25 meters and the back wheel radius is 0.4. And she's initially traveling at 20 meters per second at the bottom of the hill. So here she's going 20 meters per second. And then she gets up here and stops. And the time interval involved, the time interval involved is 4 seconds. Okay. Now, the angular velocity of each tire, remember in that lecture that we missed and had to watch on video because of Thanksgiving, right at the end, we talked about rolling without slipping. And we found by looking at an example with the Svensson brothers, the quintuplets, that what we found was that the linear velocity of the car or skateboard or bike, in this case, skateboard, is equal to the angular velocity of the wheel multiplied by the radius of the wheel. And if you look at the, I gave on Max a picture of the front page of your exam, the equation sheet that you're going to have on your exam. And that's the equation that's there, right there, okay? And so we're just going to use that to find the omega of each wheel. We know that the linear velocity is 20 meters per second. And if I look at the front wheel, let's look at the small wheel. That's going to be the radius of 0.25 meters times the omega of the small wheel. Well, if I just divide both sides by a quarter, that's going to give me an omega of the small wheel of 80 radians per second. Okay. Now, if I look at the large wheel, again, 20 meters per second is the linear velocity. That's the same for both. But here I'm going to have 0.4 meters as the radius of the wheel, the large wheel. And that's going to give me an omega of the large wheel of 50 radians per second. Is that okay, everyone? Okay. So how far up the hill does she travel? Well, this is a linear velocity motion problem. Delta x, a, b initial, b final, delta t. I know the initial velocity is 20 meters per second. And when I put that down as a positive number, I have chosen a coordinate system where up the ramp is a positive x direction. And then it stops in 4 seconds. And I'm looking for how far does she travel in those 4 seconds. Well, that makes the acceleration the who cares. Now, on the front of your exam, you're going to have this box with all the linear equations and all the rotational counterparts there. So you just look for the equation that doesn't have A in it. Well, there's an A, there's an A, there's an A. I look for the equation that doesn't have A in it. And I say delta x is equal to 1/2 V initial plus V final delta t. That's 1/2 times 20 plus 0 times 4 seconds. Half of 20 is 10 and times 4 is 40 meters. Through what angle does each tire travel as it moves up the hill? Well, there's 2 ways to solve this. I'll do it one way for the front tire and one way for the back tire. Okay, let's start out with the small wheel. I'm going to make my list of rotational variables. And I know that the initial omega we said was 80 radians per second. And I know that the final, when it stops, it's not rotating. I know that that happens in 4 seconds. I'm looking for delta theta, and that makes my alpha the who cares. So again, I use the equation that doesn't have acceleration. Delta theta is going to equal 1/2 omega initial plus omega final times delta t. And that's going to equal 1/2 times 80 plus 0 times 4. Whoops, spelled with a 4. And that's going to be 160 radians. Half of 80 is 40 times 4 is 160. Now for the large wheel, I'm going to use another approach. We have this rolling condition that relates the linear variable to the angular variable. Well, it works for all the variables. And so my delta x is just going to be my delta theta times the radius of the large wheel. Howdy hi. So I would just found that she goes 40 meters up that hill, and the radius is 0.4 meters. And if I solve for my delta theta, I just divide by 0.4 and I get 100 radians. Now, this particular equation is really, if you think about it, just a rewrite of the definition of the radian. The radian, you'll remember, theta in radians was just this arc length times r. And if you're not slipping, this arc length, if you think of something going down the road, if I were to put paint around this outside, when this wheel rolled once around, all the way back around, my S would be equal to how far I got down the road. Okay, so what I would say is that S is equal to R delta theta.
The kinematic equations not work for the,
What's that?
would the kinematic equations not work for this?
Oh, no, it would work just as well for the second one. Yeah, it'd work. You could use that. I was just showing that we've got two tools in our box. Yeah, you could, both of these problems could be solved both ways. For the front and the back wheel could both be solved both ways. Okay. Now we're almost done with this. What is the magnitude and direction of the angular acceleration of the back wheel? Well, the back wheel was the large wheel. So let's do what you just suggested and solve, make that list for the large wheel, alpha, omega initial, omega final, delta t. I've got this is 50 radians per second. This is 0. This is 4 seconds. And this we just said was 100 radians. Well, now we've got 4 pieces of information. There are 3 different equations that are each going to give me the same right answer. So I'm going to choose the simplest one, and that's going to be omega final is equal to omega initial plus alpha delta t. So 0 is equal to 50 radians per second plus alpha times 4 seconds. And that's going to give me an alpha of negative 12.5 radians per second squared. Now, that minus sign tells me that it's in the opposite direction. Because I put a plus sign here, I've defined a direction for my rotational variables. Since she was going up the hill, the omega initial is out of the page. Okay. And by putting a plus sign here for my 50 radians per second, I defined out of the page for rotational variables to be my positive direction. So my negative value for alpha means it's got to be into the page. So alpha is going to be into the page. And that makes sense because she's slowing down. The wheel is slowing down. It was turning quickly and then it stops. And whenever something's slowing down, the velocity and the acceleration are in opposite directions. Okay. So if omega is out of the page, alpha is into the page.
Can you find the direction?
Torque. Well, the first thing you need to know is that if you can draw the force and the position vector on a piece of paper, then the only possible directions for the torque are either out of the page or into the page. Okay, so you don't have to be really, really good at this. We've got two examples in the sample exams. We've got this example of Steve Iger. Some of you will remember that Steve got killed in one of my homework problems, not my fault, but my colleague's fault. And then he killed me in every one of his exams after that. So here, Sir Steve is trying to pull on this sword, Excalibur, and we want to find the torque about this point here. Now, the direction of the torque, what we do is I'm going to bring this down to where I can reach it. We start with our right hand at the pivot point, and then we reach out to where the force is applied. And this is the important step. This is the all-important step. I've got to turn my wrist so that I can wave in the direction of the force. You see that if I were to turn my wrist this way, waving in the direction of the force would require me to break my wrist. Okay, I got to be able to turn my wrist so that I can wave without hurting myself. That's going to force my thumb either out of the page or into the page. In this case, out of the page. Now, there was on the other exam another example. In this case, we're trying to turn this nut, and so that's the pivot point. That's where we're going to rotate things. And so what I would do here, I would start at the pivot, and I would reach out with my right hand to where the force is applied, and then I would turn my wrist so that I could wave in the direction of the force, and that gives me a torque out of the page. Now, if that force had been something like that, then I would reach out to where the force is applied, turn my wrist and wave in the direction of the force, and then my thumb would be into the page. Okay. So now you have two ways to find the direction of a torque. One way is the right-hand rule that I just showed you. The other way is to look at that force and ask yourself, what kind of alpha is that going to give me? Okay, because just like a net force causes an acceleration, so they have to be in the same direction, a torque causes an angular acceleration, an alpha. So if I know the direction of the alpha, I know the direction of the torque. Okay. So, other question? Yes, sir.
On this practice exam, it seems like there's stuff from other units. Is that the same with the on this practice test? Is something from past units?
Oh, yes, on both of them. And that won't be on yours.
Okay.
This was a, if you look at the website for Physics 105, this is the first semester at BYU where we've only had 4 units, 4 exams. Before, the way they set up 105 had you screaming through 5 units, actually 6, but I dropped off thermodynamics when I first arrived. But it's crazy. I mean, you were just racing too fast. You were taking an exam on the old stuff while you were learning new stuff. it wasn't going well. And so I got in trouble for this, but what are they gonna do to a 70-year-old man, right? I mean, take away my birthday? So, so what we did is we just moved waves to 106 and we shortened it down to, the way it was taught at MSU. You know, we only had those 4 topics. And so this exam, the sample exams, was the final exam. And at MSU, it was cumulative, sort of. Mostly new stuff, but there was some of the old. But you're not going to have any of those problems on your exam. None of the old stuff will be on your exam. That was a long way of answering that question. I'm sorry. But I did get in trouble. It's just, I just, you know, sometimes you just look for forgiveness rather than permission.
It's true.
So. Other questions? Yes, sir.
What's a radian? So when you say like,
I'm sorry.
what's a radian? So when you say like 50 radians, well, what is that? What does that
Oh, a
represent?
radian. A radian is nothing more or less than a fat degree. Okay. We're used to degrees of 360 degrees is going to be once around. Okay. And 360 turns out to be a really, really convenient number to use because you can divide it by 12, by 4, by 6, by 9, all sorts of different things you can divide it by. But it's not the natural way to describe going around. 2 pi radians turns out to be much more convenient. And if you go back and look at that video that we had the Tuesday before Thanksgiving, I gave an example there with a box dropping on a string that was wrapped around a pulley. And we found that if we did that in degrees, it was nasty. It was just a mess. But if we did it in radians, it was simple. It was trivial. And so turns out that a radian, 1 radian, is about 56 degrees. It's just, you know, a really fat degree. Okay. And you've got 2 pi of those, 6 and change, to get you all the way around the circle. Okay. But don't make it more complicated than that. It's just a different, you know, instead of using inches, you're using meters. You know, just a different unit for the same thing. Yes.
Is this question part of?
Oh, yes. How deep must you dive in a lake of alcohol to achieve a doubling of the pressure? We haven't done any sample problems. In class yesterday, we didn't do any sample problems dealing with pressure. And those problems can all be solved with this equation there, that grand pi equation there. And if we want to go from 1 atmosphere at the surface of this lake of alcohol to 2 atmospheres down here, the question is, how deep do I need to go? And so this becomes just a plug and chug problem. Essentially, I want 2 atmospheres to equal 1 atmosphere plus rho GH. If I subtract 1 atmosphere from both sides, I get 1 atmosphere is equal to rho GH. If I solve that for H, I get 1 atmosphere over rho G. And 1 atmosphere is 101,325 newtons per meter squared. We call that a Pascal. Rho, we were just told, was 790 newtons per meter cubed. And G is going to be 9.8 kilograms. Oh, no, I'm sorry, this is kilograms per meter cubed. And this is gonna be meters 9.8. Boy, it's late. Oh, man, all sorts of mistakes. Did you see each of the mistakes that I made? Okay. Remember, if I get to 3 mistakes, you get your tuition back. Okay, I think that was only 2 mistakes. 1, 2. So I better not make a third one here. So anyway, you see that the newtons cancel and the kilograms cancel, and I end up with meters cubed over meters squared, and that gives me meters. Okay. Well, oh, was there another question?
Question. What do we need to know about moment of
Well,
what do we need to know about moment of interest?
The figure skater, why do they spin faster? The fact that they are on ice where there's very little friction gets rid of the external torque. And we found that if I could get rid of the external torque, then there's this quantity called the angular momentum, L, that is conserved. Now, just like linear momentum is mass times velocity, mass is how hard it is to get it going, and V is how fast it's going. Well, angular momentum is how hard it is to get it turning, that's the moment of inertia, times how fast it's turning, that's omega. And unlike this equation, I can't really change my mass without cutting off an arm or diet or exercise. But my moment of inertia, I can easily change because it depends on where the mass is relative to the axis of rotation. So by pulling my arms in and my leg in as I'm turning, I make my omega, my moment of inertia small, so my omega has to get big. Now, that was not a third mistake. No, I just stuttered. Okay, the L has to stay the same. The angular momentum stays the same, but the omega doesn't have to stay the same because I can change my moment of inertia.
Do we have to calculate those problems?
What's that?
Do we have to calculate problems like that, or is it just conceptual?
Just conceptual, yeah, because we don't have we didn't practice finding what a moment of inertia was for a different shape. And so it would just be, does it get bigger, does it get smaller sort of questions. And in this case, if I ask you, does the angular momentum get bigger or smaller? What do you say? What is it? Stays the same. Yeah, that's the whole thing about being conserved, is it doesn't change. If I ask, does the omega get bigger or smaller? It gets bigger because your eye got smaller. Okay, we're out of time. Good luck. Good luck on that exam, and please try to keep calm.
Wow.